All right, good morning. How's everybody doing today? Cool. Someone's alive. Awesome. All right. Um, First thing, if you did not turn in homework 6, send me an email right away. Let me know what's going on. Um, I'm missing homework 6 from about 20% of the class. So, if I did not get your homework 6, you have a 0 in Canvas right now. That's your indication that there is a problem with submission. Get in touch with me right now through email and let me know what's going on. If you don't have an actual 0 in Canvas, it means I haven't graded it yet because I haven't graded the homeworks, obviously. But if you actually see a 0 there, it probably means I didn't get your submission. Send me an email right now. Let me know. All right, so questions about anything. I'm going to go through ODP 452, so we'll do questions on that shortly. All right, well, let's go through the ODP. Section A was extremely quiet this morning, so hopefully people are awake by now. So 452 was like 450, but we had stateful code. Yeah, we are section B. At least that's what I've been calling it. So yeah, pretty much the same code that we looked at yesterday in pseudocode. 450 basically copied from in into old. Set an output location called J, go through every character in the input, including the null terminator. And if the character is not an X, copy to the output string, which is called in, and increment the output location. Okay, 452, the big difference is we will copy the character if the input character is not an X or if this done flag has been set. So if done is set, we're always going to copy. If our character is not an X, we're always going to copy. Done starts off at 0, so the first time we hit an X, done will be 0, that'll be false, we won't copy. But as soon as that happens, we'll go ahead and we'll set the done flag to be 1. And that flag means literally we are done skipping X's. Okay? So first time we hit an X, we won't copy it, but we'll set that flag, and then every time we come through here, even if we find an X, this flag which says we're already done skipping will be true, and we'll go ahead and copy the characters. So that copies everything except the first X. And this notation is legal in C, and it's extremely common, and it takes the place of not having a Boolean type. So the original version of C did not have Booleans. But anything that looks for a condition, anything that expects a Boolean, will basically treat 0 as false, non-zero as true. So we can mimic the effect of having Booleans as long as we use 0 for false and then non-zero for true. Typically 1 or -1 is used for true, but anything other than 0. So that's a legit thing to do in C. It's not legitimate in Java. Java will complain if that's not a Boolean. Alright, so that's really all there is to 452. I did not post an ODP for today. we'll call it good for the week, and we'll start back next week with some more string-related ODPs. Homework 6 was turned in today. Your next programming assignment will probably post at the end of next week. And I think we're going to go back to a bash assignment for the 4th big programming project. Next week I want to get back into talking about bash, and I want to talk about more advanced aspects of scripting, including arrays. I want to talk about associative arrays, reading from files, a few other things like that. Maybe talk about standard error and redirecting. And then move into talking about some of these powerhouse utilities like awk and sed that let us do really powerful sort of string manipulation on input files. So we'll spend at least a week talking about bash again. This is week 6, that'll be week 7, and then we're up to basically 4 weeks left, with one of them mostly missing for Thanksgiving. So we're coming up to the end of things pretty quickly. We will have a 5th programming assignment, which I don't know if it'll be C or bash, but it'll be a good one. All right, so let's continue playing with GDB, and let me see what I got here. All right, so let's look at clean 3. So clean 3, so this is sample code for ODP 450, okay, not 452. So make our for loop. If our character is an X, we'll continue the for loop. Otherwise, we'll copy our output into our input, and go from there. So let's test this. So I'll run this, I'll say hello, and it turns into an empty string. And I'll do haxax, and that turns into an empty string, and everything seems to turn into an empty string, including an empty string. So something is wrong here, okay? So let's take a look at this. So I'm going to recompile with the G switch to say let's include debugging information. I'm going to run GDB on main. Alright, so I'm going to put a breakpoint at my clean function, and I'm going to say run, and it's waiting for me to type input. I'll type in some input, hello, and now I'm at the beginning of my clean function call. My argument was hello, and let's go ahead and step through this. So I'm going to use the next command to step. First thing says copy new to old. So if I execute that and I print old, old should be a copy of my input, right? It's HELLO, null terminator, and then whatever happens to be in memory. String copy only copies up to and including the null terminator. Outlook is 0. We're about to go into our for loop. We're about to see if old bracket I is equal to X. So let's look at I is 0. Let's look at old bracket I, that's the letter H. But it didn't do any of the stuff that I was expecting it to do. It didn't copy my character into the output array. It went back to the top of the for loop. So let's execute that. Let's look at I. Let's look at old bracket I. Well, that's the letter E. Here's my new array. And again, it skipped over the for loop. So it's not copying any of my characters, even though my code clearly says, you know, if my character is equal to an X, I'll continue, otherwise I should be doing this. And output location has not changed, and it's just not clear what's going on here. And then I exit my loop and I terminate my string. And if I look at new, well, my new string is empty. Why is my new string empty? Because my output location is still 0. And the way my code is written, it should put an null terminator at the end of the output string. And we never wrote anything into the output string. So what's going on here? Why is my for loop not executing this statement? And if you're not sure what's going on here, right, while you're desperately trying to figure this out, you might decide to take another look at your incoming argument and discover that your incoming argument changed to 5 X's. And that's a little weird. So let's run this again. I'll say hello. Alright, I'll run this again. Here's my original string old, that's hello. I'll go ahead and I'll say for I equals 0 to X. I'll check old bracket I, that's the letter H. It skips that. I'll check old bracket I is equal to an X. My old string has changed. That first character became an X. What's going on now? It's the hardest bug to find in C, and it's just been like totally exposed to us through the debugger. Why did old bracket I change to X? Because I don't have a double equal sign, exactly. It changed because I told it to change. I said old bracket I gets assigned the value X. And that's exactly what it did. Right? Now that's a hard thing to find just by staring at your code. But when you run this thing line by line and you look at everything that's happening and you see that, you know, through no fault of your own, my character in my old array has changed, that forces you to look differently or more deeply at what's happening, and that can help you see, oh yeah, I can't believe I did that again. I used a single equal sign. Alright, so that's you know, an example of where GDB can sort of help keep you honest. So I'll quit out of here. I'll go back in here. I guess I'm still editing it. Oh, I'm cheating on you. Alright, so I'll go in here and I'll change this to a double equal sign. And then I'll try this again. Well, that's working better. I was going to keep asking questions until you got it, yeah. Okay, so you know, it's removing the letter X, but it seems to be messing up my first character and some other stuff. So something weird's going on here. Let's see, question, is there a practical reason for the C standard compilers allowing that rather than producing a compiler error? Is there any practical use for the case if X equals Y? Yeah, there is actually. I use this all the time. Right, I might want to I mean, you could do something like this. Right? So this says go ahead and execute this function, take the return value and save it in this variable, and then if that was non-zero, go ahead and do something. It's not as convoluted as I'm making it look. There's cases where this is a fairly readable thing to do. But Java, for example, will call you out on that. It'll detect a single equal instead of a double. And some of this stuff in C, I don't know this for sure, this has just always been my working assumption. Some of the stuff that C lets you do feels like it was a nod to the realities of running code on, a CPU, where, doing an increment is faster than doing an addition of 1, right? And so doing a plus plus would tell the compiler you can convert this statement into an increment, whereas doing something equals something plus something would say, pull these two things, send them to an add instruction, and so on. And this feels like the same thing to me. Like you can do this assignment and believe that your status bits have been updated, engineering 270 here, right? So we did a move from here into there, and we believe the status bits have been updated, so now we can just go right into a conditional jump instead of having to interrogate some memory location to touch the status bits. I don't know if that's what they did or not. All right, so yeah, so let's GDB this. Oh, nice, yeah. Okay, good comment in chat about putting constants first when you do comparisons to help catch a mistaken assignment statement. All right, so let's go into our debugger. Let's break it. Our clean function, let's run. Let's put in a test string like hello, and let's start nexting through our code. So we'll copy new to old, we'll set our output location, we'll go into our for loop, we'll see if our first character is an X. It's not, we're about to save it into our output string. Alright, so now let's check some stuff. Old bracket I is an H. Output location is a 0. Let's go ahead and execute this instruction. And if we look at new, we can see something's wrong already, right? Well, our output location is 1, but at the time we did this assignment statement, we checked output location. That was cleanly a 0. But it appears that this assignment statement actually stored that H in location 1 instead of 0. And so we can loop around again. And we can look at old bracket I, that's the letter E. We can look at our outlook location, that's 1. We can look at new, it's HHLLO. We would expect that E to be stored in position 1. But when we do that, we see that it got stored in position 2. Right? So we go away, we take a walk, we come back, we look at this again. What the heck's going on? And someone in chat got it. The plus plus outlook, that's a pre-increment. That says first increment the value of this variable and then use that new value as the index. So even though outlook was 1, when we executed this instruction, first outlook changed to 2, and then we said new bracket 2 equals that character E. That's why it ended up right there. And you can hear me talk about pre-increment, post-increment. You can watch videos on it. You can see discussions. You can see flame wars on this, right? But when you encounter a problem like this and you find it by going through the debugger and it, cost you 20 minutes of staring and scratching your head before you suddenly realized, oh, that's what a pre-increment is as opposed to putting it at the end, right? You're going to know that for the rest of your life, right? That's where it gets tied into all sorts of connections in your neural pathways, and this becomes, conceptualized in a much deeper way than just kind of hearing it or seeing it in the textbook. So going through the debugger, right, this is part of the learning process. And personally, this was how I learned a lot about programming, was just spending my time in the debugger and working through code, taking things apart, changing them, putting them back together, seeing what happened. Sometimes with horrifying effects. That's another story. So this is a good learning tool. All right, so let's keep going with this. All right, so yeah, horrifying story. So engineering school as an undergrad. This was in an era where there was one computer for the whole school, right? And everybody used that. And we had a machine called a VAX 780. We had one of the first VAXs in production. The VAX was probably the most popular mini computer of the time. Everybody had to have one. Well, we had one before most other people, including a lot of government agencies who were still waiting for theirs. So, you know, I liked exploring what would happen, and, you know, I kept getting seg faults when I tried to access location 0, and I was like, what's the big deal about location 0? So I gave myself basically root access and wrote a program to throw a value into location 0 just to see what would happen. And if you get a seg fault like that while you're root, it would cause the equivalent of a panic. This wasn't Linux, but the equivalent, and it would basically reboot the system. And, you know, there are no CRTs. Everything was on a line printer, so the information from the reboot would print out on paper. And I was just doing this for kicks, and so I, you know, just called the program one of my favorite 4-letter words for program names. And I tried this, and the machine crashed. And when it crashed, you know, the printer started printing out all of this information, everything about the system status going on and so on. Well, there was a visitor, a very important visitor to the school, who was touring our computer room at that moment and was in the room when this console started printing out all this information, and it was getting very exciting. And so he wanted to see what it was all about. And here comes, you know, line after line mentioning the name of my program, which was an obscenity, and that kind of caused some issues, aside from the fact that I crashed the school's machine by playing around with, you know, doing privileged things just to experiment. So don't do that. I don't think I ever told anyone that story. All right, so let's look at clean 4. So same thing, we've replaced this with a double equal sign, so we won't get into that trouble again. Let's try this. I'll compile it with G because I have a feeling it's going to have a bug. So I'll run main and I'll say hello, and that seems to work great. All right, I'm done, right? Walk away, turn this in for my grade? No, let's test it some more. Let's try hi. Let's try an empty line. Let's try hacks ax. Well, that didn't quite work. So my 2 A's seemed to change into 3 A's, and I got an extra X at the end. Well, that's a little weird. Oh yeah, location 0 is deliberately made to be inaccessible because the most common error that you make when you're dealing with pointers is you forget to initialize something. And so rather than just let your code do whatever, usually most machines set up location 0 to be inaccessible. But the assumption is that kernel level code that's running in a privileged mode, should not be getting seg faults. And if that happens, the system assumes something got corrupted somewhere and it reboots itself. But, you know, with great excitement and flurry and lots of output produced beforehand. So yeah, I learned what location 0 is all about. All right, so what's going on here, right? It seems to be working in some cases. And you know, in other cases it doesn't. So let's run this in the debugger. I'll put a breakpoint at clean. I'll say run. I'll just say HAX, and I'll start stepping through this. So we'll copy new to old, set our output location, check the first character, that's not equal to I, it should copy that into new and bump up our output location. Alright, let's just check some things now. So output location got incremented to 1, new begins with an H, that's good. Let's continue stepping. We're going to look at the second character, which is an A, that's good. It's going to copy that to our output location, increment output location. We'll come up to our third character. And in this case, old bracket I is an X, so it should not copy to our output string. So let's take a look at our output location. That's a 2. Let's go ahead and execute. We do the continue statement, that's good. And we come back up to the top of our for loop. And now we exit our for loop. And that's the end of our function. Well, if we look at the value of our variable buffer, it's got this X sitting at the end still. Even though we did not copy that. Right? We saw there was an X here. We didn't do the copy. We went to the continue and we skipped out. And we confirmed our output location was 2. So, you know, if it was going to copy a character, it would have gone here. But it didn't. But the X is still there. So let's run that again. So let's just try an X. Alright, so here's our old string, that's an X, here's our new string, that's an X. Our output location is 0. We're going to go into our for loop. If the old character is an X, we're going to skip everything. It does that skip. We come back to the top of our for loop. I is a 0, so when it increments, it will be bigger than the length of our string. We kick out of the for loop and we return. And if I look at buffer, it's the string containing X, even though we didn't copy it. So now we have a really pared down minimal test case. So let's do that one more time. Let's just put in an X. And let's just watch the flow of our code. And that's it. It's going to return to our caller. So what did our function do? Copied new to old, initialized an output location, started our for loop, decided not to copy the X, reached the end of the for loop, and returned. So what do I really expect the value of my string old to be at this point in my code? Exactly the same thing as my starting string new. I haven't made any changes to it. So of course, when I get back, my string is completely unchanged and it still has that letter X. So now you go back and you look at your algorithm and you look at your notes and your pseudocode or whatever and you say, okay, why didn't my algorithm make any changes to my string? So what's wrong here? And this one's a little harder to find, but maybe you run through this on paper and you think about, what was I thinking when I wrote this code? I was only going to copy the characters that were not an X, right, and bump up the output location. So So let's put in a bunch of things in our string, and let's step through this. And there's no copying happening anywhere in sight. It's continually skipping my x's, which is exactly what it should do. There's my new string. It's a bunch of x's. Hey, there we go. We don't have a null terminator. This is an edge case around an edge case, right? We started off with a new string, right? And we told our code each time you find something that's not an X, write it into this string starting at the beginning. And our code never writes anything, but if we don't put the null terminator on there, our string is, you know, still the original value of the string. All right, so so there you go, missing null terminator. The replacement actually was conditional on the if x. So if the input was x, it would say continue, which goes back to the top of the for loop. Otherwise, it would do the replacement. Let's see, is answer a protected place in memory? Do I actually use the word answer? I don't know where answer comes from, but no, it's not. Not per se. Which one was that? Clean for. So let's just change this to go less than or equal to. Alright, so that seems to work. Interesting. So you used ANS instead of answer. So I don't know any reason why that would happen, but I'm guessing maybe there was something else named answer, maybe? Oh, you're talking about the program name itself. So answer is the name of a command in on the Linux system, and if you name your ODP the same thing as a command, and then you try to assess it, well, the assess doesn't have the same path that you have, and so it will end up running a different command than the one you're trying to assess. So yeah, don't call your program answer, don't call it test, don't call it read or echo or GCC or any other built-in command. Oh, as a variable. Well, then I have no explanation. If you have that code, send it to me offline and we can look at it, because that seems interesting. So if you try to do something like this, we say buffer equals this string, and try to run that through your code, you'll get compile talkback, because I declared my buffer to be an array, and then I'm trying to assign it the value of a string. So this is just kind of weird. But if I set up buffer to be a car star, right, this will run, but I'll get a seg fault. So let's break it clean. All right. So as soon as I get into clean, oh, I didn't expect that. Oh. This is an even better example. Okay, let's all right, so let's just do this. Let's just set buffer equal to a string, call clean, and then print out the value of buffer afterwards. Right, and that gets me a seg fault. So let's GDB it. Let's put a breakpoint at clean. Let's run it. So we're inside our clean function, and our argument is this string. Okay, so let's single step it. So we're going to copy from our argument into old. So there's our old string, and we'll set our output location, and then we'll go through and check the old character. It's not equal to an X, so let's copy that into our new. So let's print I. Let's print old bracket I. That's the letter H. Let's look at our output location. That's a 0. Let's go ahead and try to copy that H into our output. There's your seg fault. All right. And this is potentially confusing, right? Because that's our array new. If I look at new bracket 0, that's an H. If I try to copy a value into that by hand, oh, that shouldn't have worked. Oh, that worked. Bad example. All right, that was not helpful. But let's just look at this, right? This statement threw a seg fault. Okay, you can find this by putting prints in your code and see what the last print is before you get the seg fault. But something's wrong here, okay? This is subtle. The difference here is when you initialize a string to be a literal like this, that literal is placed in a protected area of memory. The assumption is you don't want to change the contents of this string. And so in our code, when we try to write into that location, we get a permission error. That's what a seg fault is, basically. Confusingly, GDB will actually let me change that value by using a set instruction. That's kind of unfortunate for the demo. But this is just something you need to know. When you declare a string as, double quote, string, double quote, that's not a writable string anymore. So if I wanted to do this same experiment, but I wanted my string to be writable, I could have done this. Could have done a string copy of that string into buffer. And that reads the characters one by one and saves them into this array, which, since I've declared it to be an array of 120 characters, that's a writable chunk of memory. And so if I run that, it works fine. So this starts to get into the idea that even if you think of yourself as a pure coder, you don't want to deal with the hardware and the registers and all that. You're just a coder, right? There are places where you need to understand what's going on the hardware side of things. There's interrelations between the memory management system and how the memory is configured and what you're going to do in, say, a C program. So you can't be purely a software person, and if you're purely a hardware person, that's great, except that your hardware is filled with software, and sooner or later you're going to bump into that. So there's a lot of overlap, and this is part of what 270 is about, right? Is looking at the connection between the hardware and software sides. All right, so let me fix my main program. And let's see, we're doing... Yeah, that looks good. All right, so our main program is fixed. So clean 4 looks like it's good to go. So let's look at one more. So we've cleaned this up. We're including the null terminator by looping as long as we're less than or equal to the length of old. We're not doing any funny pluses anywhere. We've got the null terminator in place. Let's go ahead and test this. So I run hello and my string gets truncated. And when I do AX, it gets rid of the A, but it keeps the X. And if I do XA, it keeps the A, so it looks like it's getting rid of the first character. But haha, it's getting rid of the whole thing. So you want to run some test cases, right, and see if you can try to get an idea of what's going on just by looking at the behavior of your code. But it's not clear what the problem is here. So let's GDB this. Let's break it clean. Let's spell it right. Let's run it. Let's put in ABC. All right. So our function is being called with ABC. And by the way, you notice the address of my argument 7FFFFFFEA60. Up here, when we were having these problems, the address of my argument was 4007C4. When you see numbers like this, think that's... let me put it this way. When you see numbers like this, those are local variables. Okay? Something with 7 and a bunch of F's, that's a bunch of 1s in binary. Okay? That's typically where your stack is. So we have a stack, and we use the stack to store local variables. So when you see an argument whose address is, 7FFF something, it's probably a good solid local variable. When you see something like this, 4007C4, something that's not, a bunch of 1s, that's a different kind of variable. This was something that was allocated as, a dedicated constant, basically. That's something you just start to notice over time. So this is a good local variable. We should be able to read this and write this, no problem. Let's go ahead and run through our loop. We'll copy new to old. We'll set our output location to 0. We'll start our for loop. We'll check to see if our character is equal to X. So let's print out I. That's a 0. Let's print out old bracket I. That's the letter A. Exactly what I expected. Okay. So if it's not equal to an X, if it is an X, it should continue. If it's not an X, we should go ahead and copy our character to our output, bump up the output counter, and then go back to the for loop. So let's go ahead and execute. Well, it went back to my for loop. It didn't seem to do the copy. So let's check old I. Well, let's look at I. I is a 1. If we look at old bracket I, that's the letter B. Okay, that should get copied back to the top of our for loop. I is now a 2. If I look at old bracket I, that's a C. Well, that should get copied. Someone said check Outlook. Outlook is still 0. Hasn't been incremented. If I'd done my copy, it would have incremented Outlook, but it doesn't seem to be doing my copies. Go back to the top of our for loop. I is a 3 now. We look at old bracket I, that's our null terminator. That's not an X, so that should get copied. But it goes back to the for loop again, and now the for loop exits. And now we say new outlook equals old I. Well, old bracket I is an all terminator. Output location is 0, so when we make that assignment, new just changed into an empty string. And then we bump up outlook and we return. So what's wrong with this? We looked at it step by step and we saw very clearly that this character was not equal to an X, so it should not have been doing the continue statement. But it appears that it did, because it kept going back up to the top of the loop. And this is a really subtle problem. Yeah, awesome. There's a missing bracket here, right? Normally we put a bracket at the end of our for statement. I don't have a bracket there. If you say for or while or if or something like that and you don't put a bracket after it, the body of that statement is a single instruction. In this case, the whole contents of my for loop is one if statement. So the only thing my code does is go through my old string, and if the character is an X, continue. Otherwise, it goes back and continues anyway. And it was only when it exited the loop that it went on and did these lines of code. In other words, this code's outside my loop. And I had a hint for that because while stepping through my code, it just kept doing my loop, my loop, my loop. And then at the very end, when I was equal to 4, it went ahead and did my assignment and my increment. So that's a really sneaky thing to find. Now, if you have the habit of always putting brackets after your code no matter what, then you're not likely to make this. But if you thought you only had one thing to do and then you added some extra stuff and you didn't have brackets, you might forget to have the brackets in. Doesn't VI highlight the opposite bracket to make this less common? You can set it up to do that. The problem is that some editors do so much highlighting that it can actually obscure what's going on, because a lot of stuff that's highlighted is not an error, and there's nothing inherently erroneous about this. But yeah, that can help. Now, indenting is another subject here, right? So if you were indenting this by yourself, right, you probably wouldn't have indented without putting the brackets in there to begin with. But if you have an indenter that's absolutely perfect, then this stuff would have been moved over to the left, and you might have noticed that. But a lot of indenting will do, you know, whatever the previous indent level is and so on. So this can be tricky to find. But GDB, right, or some sort of debugger can help direct you to where you should be focusing your attention. And imagine, you know, 1,000 lines of C code, and all you know is the final answer coming out at the end is not correct, right? Well, if you can narrow it down further and further and further and get down to the fact that this function call is not doing the right thing, and when you run it, you know, it should be copying all my characters, but it's not copying any of them. And then, oh yeah, at the end it copies one character, right? That can force you to look at that section of code, and then you go away, you come back with fresh eyes, you look at it, and you'll see, oh yeah, I don't have brackets there. All right, so that's just some of the examples of what a debugger can do for us. When you're working on a project, if it's not due like right away, right, if you got time to spend trying to dig into the problems, pull out GDB. Get a quick reference guide or just make some notes and start trying some commands and just see if it works for you. The more you play with it, the more useful it becomes. So that's something to mess with. The GDB comments I made in the previous section, we talked a little more about some of the other things you can do with GDB for doing assembly language debugging and so on. So if you're interested, go ahead and take a look at towards the end of the Section A video. All right. We will go back to talking about scripting and bash and more interesting bash constructs starting on Monday. Have a good weekend, and I will see you next time. Thanks.